Hello everyone and welcome to MP Tutors. I'm Solo and I'll be looking at question 1 for the physics paper. Okay, paper 1. And let us get to it. While I am going there, please don't forget to like our videos and subscribe to our channel. Don't forget to tell your classmates about us, especially for those in Gauteng. I'm catering to you right now. So yeah, we are aiming for 2,000 subscribers. We're at 1,420 at the moment, so I'm only doing question 1, and once we get to 1.5 I'm gonna load more questions. Okay, so we're helping one another out here, us getting more subscribers, you getting knowledge and a memo for the test you just previously wrote. Okay, so now question 1. 1.1, which of the following best illustrates balanced forces? Okay, so A, a person lifting a heavy object from the ground. Okay, so they lifted it from the ground to wherever. That is work done, basically. That would be force times displacement. Doesn't really tell me about balanced forces. Then B, a big rock, free falling to the ground. Again, the only force that acts on that rock is gravitational force. And then C, a light stationary object. It's stationary, okay, so it must be sitting, standing on something. And if it is, I'm just gonna put like a brick on a table or surface or something. So we know we would have our gravitational force and we would have our normal force. So that's balanced, right? Cool. And then a force on a box, a force of a box on the earth and a force of the earth on the box. So basically the center of mass, center of mass of the box to the earth, and the earth as well, the center. So basically here we're using gravitational force, right? What do you call it again? Newton's law of universal gravitation. Okay, and with that, balanced, I'm leaning more towards C. Okay, the stationary object. And then 1.2, an 8 kg box is placed on a rough surface as shown below. Okay, so assuming that this is the 8 kg, since I have a sketch already, so 8 kg, and then we have an applied force. Okay, if applied, let me just use a different colored pen to just show that I'm doing question 2 using question 1's sketch. So we have an applied force, okay, and they told us is 16,5, and then we also have friction, okay, because it's a rough surface, and they tell us the acceleration, right? Now they say if a force of 16,5 Newton is applied to the box, it accelerates at 1,5 meters per second squared to the right. So your friction can't be bigger than your applied force. This arrow should actually be longer and this one should be shorter, just to show magnitudes. I don't think they're strict on that though, but just saying. Okay, so the frictional force between the 8 kg box and the surface is, so we know here we have the net force, right, is equal to mass times acceleration. The net force is your force applied minus your frictional force, or Fk, kinetic friction. Your mass is 8 and your acceleration is 1,5. So if we want to get the frictional force, it'll be 8 times 1,5 minus the applied force, which is 16,5. Okay, and then let's see if we calculate that, what are we going to get? My calculator is, it was doing its thing there. Okay, it paused. So we have 8 times 1,5 minus 16,5, and we have negative 4,5. But if we now look at the positive, it's going to be 4,5 Newton. Okay, and that is B. Alright, let me just go back to my blue color. And then 1.3. So a ball is dropped from a certain height above the ground and bounces a few times as it hits the ground. The velocity time graph below describes the motion of the ball from the time it is dropped. Okay, so basically if you were to draw a displacement time graph, or just in general thinking about it for the visual learners like me, you have your ball, okay, it is dropped to the ground. So basically it will reach the ground, right? So that would be at 0 there, where velocity is 0 because it's dropped, it wasn't thrown. And then once it reaches the ground, that is A. And then the dotted lines basically indicate the time that the ball has spent with the ground before it goes away, okay? So from A to C, basically, you have the time spent with the ground. And then it goes back and bounces, okay? So it reaches its maximum at D, okay? Because maximum, that's where there's 0 velocity. Okay, and then, yeah, it doesn't matter now. Now let's look at the question because I've plotted A, B, C, and D just to explain what's happening. Now it says, in relation to the velocity time graph for the bouncing ball shown above, which statement below is correct? A, oh, another thing. You can see here, down is actually negative. If down was taken as positive, your graph would have been like this. Okay, your velocity would have been positive. So for the fact that your velocity is actually negative shows that down is taken as negative. Upward was positive in this case. So now if you look at the questions, down is taken as positive? No. So we're going to look at the options where down is negative, right? So down is negative for option C and D. Now it says, down is taken as the negative direction and the ball is at its highest position of its bounce at C. No. At C, from A to C, it's the contact time with the ground. Okay, but at D, that's when it reaches its highest point. So I would go with option D. Okay, because down is taken as negative and the ball is at its highest position of its bounce at D. Okay, so that is 1.3. Now we look at 1.4. Two identical solid spheres, each with a mass of m or mass m and traveling at a speed v, move toward each other in an isolated system. The spheres have a head-on elastic collision. So remember, if you have elastic collision, it means the sum of the kinetic energy initially is equal to the sum of the kinetic energy afterwards. Okay, so basically, yeah, it's conserved. All right. So yes. Now, which statement is correct for the collision as described above? So what will happen? You have your initial phase. Let me just say initial. And then you have final. All right. So initially, okay, we have sum of kinetic energy initial, that is equal to sum of kinetic energy final. So we don't really have information about what happens at the end. Do they stick together? Do they go apart afterwards? We don't know. But we know what happens initially. Initially, the one, is it a ball? A sphere. Solid sphere comes, the other as well comes. So we have half m1. Okay, I'm just going to call the one on the left 1, the one on the right 2. So half mv. The v, if I take going to the right as positive, so that will be positive v squared plus half m2, and the other one is going that direction, so it will be negative v squared. Now obviously positive number, negative number, as long as you square it, it will be positive. So half plus a half, I will have mv. Banana ventures. mv tutors. You'll have mv squared. Okay, and that will definitely then be equal to your final kinetic energy. So it says, which statement is correct for the collision as described above? The spheres stick together on impact. If they stuck together on impact, it means the final kinetic energy would be 0, right? Because it would be stationary. Sorry for the noise. It is what it is. It says the total kinetic energy after impact is mv squared. Yes. The total kinetic energy before impact is 0. No. The total momentum before impact is 2mv. No. So our answer would be B. And then 1.5. The mechanical energy of a moving object will remain constant if... Okay, so mechanical energy, E mech, is basically equal to the kinetic energy plus potential energy. And what is that? That will basically be half mv squared plus mgh. Now, if you think about just an example of mechanical energy, you would think about maybe a slide, okay? Or even a roller coaster, okay? But basically, your starting point and your final point, whatever happens in between, guys, they could literally have done this. But it ends there. So, okay, maybe that's a bit extreme. But anyway, you catch my drift. So if we're looking at mechanical energy, that's what comes to mind. I'm thinking simply a slide, maybe a roller coaster. But yeah. So they say the mechanical energy of a moving object will remain constant if there are frictional forces present. So if there's friction, now we're looking at non-conservative forces. Okay, so I don't think mechanical energy there will be constant or conserved in an isolated system. And then for B, it says there's only gravitational force acting on it. If you look at your formula, yes, the only force acting on it is gravity. C, only the kinetic energy remains constant. No. both kinetic and potential energy, are isolated. So only the gravitational potential energy remains constant. No. So the answer that we're going for would be B. Okay. Now 1.6. A train is moving at a constant velocity of 10 meters per second. So the velocity of a source, if I see train moving, I see velocity, I see frequency, I know we're dealing with Doppler effect. So velocity of the source is 10 meters per second. Actually, let me just read the whole question because now I'm assuming the train is going to produce some sound. So a train is moving at a constant velocity of 10 while sounding its whistle, which has a frequency of 500. Okay, now I can write with confidence. Velocity of the source is 10 meters per second, and it has a frequency of 500 hertz. Okay, take the speed of sound in air as 340 meters per second. What frequency will be heard by a man sitting in the train? If a man, so that's the velocity of the listener. If a man is sitting in the train, do you guys agree that the man has the same velocity as the train? So they will also have 10 meters per second. Still, the speed of sound is the same. Okay, now it says, what frequency will be heard by a man sitting in the train? Okay, are we expecting it to be more than 500 hertz, less than 500 hertz? No sound will be heard. That's not possible. Or will it be 500 hertz? Okay, remember how the equation looks? I don't even know if the equation will help us at this point, because the equation has to do with one source moving. Like, is another person moving? Or is the source stationary? Oh, when are we getting to the formula sheet? Okay, where is Doppler effect? There it is. So basically, the frequency of the listener is equal to the velocity of A, which is 340, plus or minus velocity of the listener, which is 10. So the velocity of the listener is 10, the velocity of the source is 10, the frequency of the source is 500. We have plus minus on in the numerator and also denominator. So what do we choose? Plus minus depends on whether the source is moving away or moving towards, or whether the listener is moving away or towards. In this case, they are like joined together. They're like one. So in a case like this, where both are moving at the same speed, there's a sound produced while they're both moving in the same place or whatever, then in this case, the answer would be A. Okay, the frequency heard by the man would be 500 hertz. And if you want to use maybe waves to show that, you basically have the train and the man inside, and so the waves coming out, the wavelengths will be equal for both of them, and that is why they hear the same frequency. Okay, yeah, took a while there to explain that one, but I hope it makes sense. 1.7. Okay, the diagram below shows a point P at a distance r from a charged sphere. The electric field strength at point P is, so remember, electric field strength is equal to the force over the charge. Ooh, let me just make sure I'm not telling lies. Okay, electric field strength would be F over Q, but I prefer this equation better. KQ over R squared, because if you take F is K times Q1 times Q2 over R squared. Okay, so that's basically that. Now what are they asking us? Okay, 1.7. The electric field strength at point P is directly proportional to R and to the right. Okay, now let's determine direction. Okay, because if you have Q over there, which has a negative charge, remember a negative charge, if you have your sphere, the electric field lines point inwards, okay, and you have P over there, okay, so the direction will be towards left, okay. So I'm going to look at the options where the direction is left, which is B and D, okay. So now it says electric field strength is directly proportional to the square of R. No, I mean, if you look at this, if I increase R squared, E will decrease. So it is inversely proportional to R squared. Okay, so we know it's moving to the left. So it is inversely proportional to the square of R and to the left. Okay, it's going to the left. Yeah, so it's D. So that is 1.7. And now we get to 1.8. Okay, so which of the following statements about an AC generator is true? The minimum potential difference. So remember alternating current, it's this one here, where you have a wave, right? So this would be the period of the wave, and yeah. Okay. Sorry, I think someone is knocking. I'll be. Okay, I'm back. All right. Yes. Which of the following statements about an AC generator is true? I've sketched for you alternating current. The difference between it and a DC current does this. Okay, this would be your Vmax, Vmin. So now it says the minimum potential difference produced is not 0 volts. Okay, yeah, I can believe that. I mean, Vmin will be some negative volts or something. But ish, that statement. Then B, the EMF produced decreases as the number of windings in the armature increase. No, if you increase the number of windings, the EMF will increase. C, the maximum value of the AC can be increased by increasing the period. Remember, when you increase the period from your sine and cos graphs, it will do something like this. So no, it doesn't quite do that. The maximum value of the AC produced can be increased by increasing the speed of rotation. That is, I'm confident about that one. If I were to choose between D and A, I would go for D. Okay, it is true. If you want to increase the maximum value of AC, you do that by increasing the speed of the rotation of the coil as well as increasing the windings. Okay, two of the other ways of doing that. So I would go with D in this case. And then 1.9, we are almost there. A battery with internal resistance is connected to a fixed resistor R. A voltmeter is connected across the battery in the diagram A. Across the battery as in diagram A. The battery is replaced by one with the same EMF but with a larger internal resistance as shown in B. In diagram B, how would the voltmeter reading and the current through the fixed resistor change compared to diagram A when switch S is closed? Okay, so what would the voltmeter reading be? So with diagram B, if I were to use the formula EMF, which is your potential difference plus your lost volts, okay, your EMF remains the same. So this is for diagram A, for diagram B. Okay, your EMF is 12 in both scenarios. Your internal resistance initially was 0.2, right? But but what happened then? So we want this reading basically. So here you had a certain reading initially, but now, okay, let me not put an arrow. You had a certain reading, okay, and your lost volts were I times 0.2. Now in this case, you still have the same EMF, but your internal resistance has increased, okay. So if this has increased, it means that your potential difference has decreased. All right, so voltmeter reading has decreased. So I'm going to look at option A and B. But what happened to the current as well through the resistor? If you look at your equation, V is equal to IR, and we go I is equal to V over R. If V decreases, because potential difference is directly proportional to current, then your current will also decrease. Okay, your resistance has stayed the same. So in this case, voltmeter reading decreases, current through the resistor also decreases. So your answer is A. And then we are at question 1.10. Yes. So 1.10. The graph below shows the kinetic energy versus frequency for a photocell that has a sodium metal cathode. Then they tell us that the work function of sodium is that value. So work function of sodium is equal to 4,41 times 10 to the power 19 joules. So we can see kinetic energy, frequency. Now it says the threshold frequency of sodium is, so we want to know what is the threshold frequency. If you go to your formula sheet, if you wanted to calculate it, that is, you will see that no, somewhere above, yes, there it is. You will see that your work function is equal to the constant, Planck's constant, times your threshold frequency. So your threshold frequency would be equal to your work function over, is it called Planck's constant? Oh, now I'll be lying. Yes, it is Planck's constant, which is 6,63. So let's just calculate that and see. What do we get as our answer? Okay, so work function, it was 4,41 times 10 to the power negative 19, and the Planck's constant is 6,63 times 10 to the negative 34. Okay, so we get 6,65 times 10 to the, negative 19. And then, why is it giving me that answer? 6,65 times 10 to the power negative, or 10 to the power 14. Yes, yes. Okay, now let's go back to 1.10. Are you going to get the same answer? What will be happening? Let's see. So 1.10. Okay, now the threshold frequency. I don't see 6,65 anyway. Yeah. Actually, let me go for hertz because it's frequency. Yeah, so I don't see that anyway. So what do I do at this point? Do I panic? No, I don't. Why? Because the graph will tell me exactly what the threshold frequency is. Okay, remember, if you have kinetic energy versus frequency, there where that line touches the x-axis, that is your threshold frequency. Okay, and if I have a look at the graph without doing any calculation, I would then see that the threshold frequency is 3 times 10 to the 14 hertz. Okay, and that would be B. So I would go with B. Okay, and that's it for question 1. Please don't forget the mission. We're trying to get to 2,000 subscribers. So we'll keep releasing questions with 100 subscriber increase. So right now we're at 1,420 subscribers. So once we get to 1,500, we're going to release the next question, and so on and so forth. Thank you for tuning in. Have a lovely day further. Bye. Wow. Hello everyone, and welcome to MV Tutors. I'm Tulu, and we are still continuing with physics. The memo, prelim memo. Alright, and we're going to do question 2 today. So please don't forget to like our videos and subscribe to our channel. And let's get down to it. So, question 2. A group of learners design a device that consists of a light ball on a string hanging from the roof of a cargo truck. The device is used to determine the acceleration of the truck. When the truck is stationary or moving at a constant speed, the ball will hang straight down. But when it is undergoing a constant acceleration, the ball hangs down at an angle theta, as shown in the diagram below. Okay, that makes sense. I mean, if a vehicle is moving very fast, maybe in that direction, the ball would be at an angle. Okay, now firstly, draw a free body diagram of all the forces acting on the ball. Okay, let us get to it. So, question 2, 2.1. You have our ball over there. So firstly, we can see there's tension in the string, okay, because the ball is connected to a string. So the tension is in that direction. I don't know if you guys put it as FT, as in force of tension, or you just put a capital T, okay. And another force that's acting on the ball, well, gravity. Okay, so FG or W, I prefer putting the FG. Okay, so I think those are the 2 marks that they want. If you wanted to be fancy, you could have just indicated here that, we have theta. But yes, so don't forget to show your arrows. And that is it. That is your 2 marks. Okay, now 2.2. Okay, it says, in this case, the mass of the ball is 50 grams and the angle theta is 18 degrees. So now we need to calculate the horizontal force on the ball. Okay, so if I'm going to calculate the horizontal force on the ball, using this very same free body diagram, I will then resolve my tension force to its x and y components. Okay, so I would have ty there and tx. Okay, and since we have theta here, if you use alternating angle, this is theta, So I would say this would be t cos theta. We know it's 18, but I'm just going to put theta for now. And then we have t sine, because opposite angles. So t sine theta. All right, and they want the horizontal force on the ball. So basically we're looking for t sine theta. Okay, so what do we know? Firstly, I'm going to work out what t is. So we know that, okay, so we know that there is no acceleration in the y direction. So let me just say t cos theta minus fg is equal to 0 because there's no acceleration, right? Remember, it comes from the formula F is equal to ma, or F net. Okay, and our net force is tension and gravitational force. So there's no acceleration. So therefore I can make t cos 18, because they told us theta is 18, and then fg, that's basically going to be your mass times gravitational acceleration. So your mass is 50 grams. So you can say 50 times 10 to the power negative 3, because you're working in kilogram, and then minus 9.8, sorry, times 9.8. So therefore we have t is equal to all of that divided by cos 18. Okay, so if we work that out, we get 50 times 10 to the negative 3, or you could have said 0.05, and then times 9.8 all over cos 18. Okay, so we get that it is 0.52. Okay, please don't erase that answer from your calculator. I am rounding off to 2 decimal places, but eventually we're gonna need this answer for the next question, probably. No, we're not done answering, my goodness. So yes, I found what t is. They wanted the horizontal force. So the horizontal force is t sine theta. The danger here is forgetting what the question said. So horizontal force is equal to t sine 18. We know that t is 0.52 sine 18, and then we're just going to go back to the calculator, multiply this value, multiply that value times sine 18. Okay, and that's 0.16. 0.16 Newton, and that is our horizontal force. Okay, now 2.2.2, they want us to calculate the magnitude of the acceleration on the track. Okay, so it is accelerating in the x direction, right? In the horizontal. We said it doesn't accelerate in the vertical, it only accelerates in the horizontal. So let us see. Yeah. So basically, in the horizontal direction, there's only one force. So we know that force is equal, or rather resultant force or net force is equal to mass times acceleration. So our mass, we know that it's 50 times 10 to the negative 3. We are looking for acceleration, not acceleration. And the only force acting in the horizontal direction is the one we just calculated, 0.16. Hopefully you did not delete it from your calculator. Okay, so acceleration would be 0.16 divided by 50 times 10 to the negative 3. Okay, so we get that value, right? Oh no. What did I do? Okay, sine 18. Okay, there we go. So now our answer, we are going to divide it by 0.05. So our acceleration is 3.18. Okay, 3.18 meters. Remember, it's per second squared when we do acceleration. Okay, and now 2.3. So So A and B below are two identical blocks, okay? They have the same mass, as you can see, 5K. Each with a mass of 5 kilograms, kg, not K. Joined together by a light, inextensible string. So we're not considering the weight or the mass of the string. It's light, okay? The blocks are being pulled with a force of 65 Newton at an angle of 40 degrees to the horizontal. The two blocks accelerate to the right at an acceleration of 2.17 meters per second squared, and the tension in the rope is 26 Newton. All right, calculate the friction on each block. Okay, guys, for all the visual learners out there, we first start by doing the free body diagram for each block, because I don't see how else this would work out without one. So for A, we know that we have the force of gravity, the weight, okay, just gonna put it there, so that's 5 times 9.8, and then we have the tension force, right, which is 26, they told us, and then we have friction on the other end, okay, because it's moving to the right, we know that the friction is not bigger than the tension force. Then we have, because it is against the surface, we have the normal force. Right? Any other force? I can't think of it. We'll see as we go on. And then for B, again, we have the weight. Okay. So that's 5 times 9.8. Then we have the tension force. Okay, 26. Then we have, again, the normal force. Right, and then we have friction as well, acting, kinetic friction, that's why I put FK. I'm squeezing things. Then we have our applied force, okay, force applied, which is 65. Okay, I'm squeezing things. Okay, force applied, which is 65 Newton. And what else? Okay, so you can resolve that force into its x and y components, but for now, yeah, let's just stick to what we have. Okay, let me just rather do it now. So I know this would be, so that's 40, right? So that's cos, so that's 65 cos 40, and that one would be 65 sine 40. Okay, now let us calculate. That's why it's 5 marks. We are working here. Okay, so calculate the friction on each block. It would be easy for me to start with A. Okay, let me just do this so that I can calculate on each side. All right, so if I resolve, or rather work out the horizontal forces, remember, resultant force is equal to mass times acceleration, or net force. Okay, so I have tension because it's moving to the right, minus the friction force is equal to the mass, which is 5 times acceleration. They gave it to us, 2.17. All right, and then I know that my friction force, that will be 5 times 2.17 minus the tension force, which is 26. So let us calculate there. Okay, so I have 5 times 2.17 minus 26. So I get negative 15.15. Okay, so ultimately we know that our friction force for block A is 15.15 Newton. Then what about block B? Again, I'm going to just look at the horizontal forces. Okay, so I know that my net force is equal to mass times acceleration. So I have the force applied minus the tension minus, I should actually say that's A, that's B, and that will be equal to mass times acceleration. So again, 5 times 2.17. The force applied is 65, or let me just say that. So 65 is going to go that side, so that's negative 65 cos 40. Okay, and then plus the tension, which is 26, and then plus 5 times 2,17. Okay, what is 5 times? Okay, just gonna say plus this value. It's not fitting, guys. Okay, so negative friction force for block B. I have negative 65 cos 40. Please, when you work with angles, make sure that your calculator is on degrees and not radians, or else you're going to get wrong answers. So negative 65 times 40, let's make sure it is 65, yeah. And then plus 26, that's the tension force. And then plus 5 times 2,17, so I get negative 12,94. Alright, and so the kinetic friction for block B is going to be 12,94 Newton. Alright, so we are done with question 2.3.1. And then the final question, 2.3.2, it says explain why the frictional forces on the blocks differ. Okay, remember what the frictional force formula is. Okay, in this case, it's kinetic friction and not static. So it's basically your normal force multiplied by the coefficient of friction. Okay, so in this case, we were not told anything about the surface conditions. Okay, so one could assume that the coefficient of kinetic friction is the same for each block, assuming that it is the same material or the same roughness that these two blocks are sliding over. Okay, so the frictional forces differ because either this value here could be different for two blocks. Okay, it's a possibility. All right, so this value could be different, but for me, the likelihood of making that different, for me, I think that would be low. So I would rather go with the other factor here in terms of getting our kinetic friction or friction force. The normal force is different. Okay, look at your free body diagram. So here, our normal force, okay, which is 5 times 9.8. 5 times 9.8, that is 49. Okay, if you were to work out 49 Newton, if you were to work out the normal force here, okay, so basically it would be normal force plus 65 sine 40 is equal to Fg, which is 49. All right, so already you can see that the normal force here is different. All right, so if you had to say 49 minus 65 sine 40, that would be 7,21. Okay, so you would get different frictional forces because the normal force for both blocks is not the same. Okay, one is less than the other. All right, so yeah, so this works because it's different for each block. And you could use the calculation to further explain and to show that the normal forces are different, hence we're getting different frictional forces. Or you could also say further to that, you might find that the coefficient of kinetic friction is different for both blocks. Okay, and that's it for question 2. Hello everyone and welcome back to MB Tutors. I'm Tsilo and I will be doing question 3 with you guys. So yeah, don't forget the drill. Please like our videos and subscribe to our channel. Please do comment down below if you have alternative ways of solving the solution. I really do like the interaction that we have. And also, yeah, share this info with your classmates. Remember, we are aiming for those 2,000 subscribers. We can do it, right? Yeah, so question 3. It says a 50-gram ball is dropped from a certain height. So if it's dropped, we know that initial velocity is 0, and we can see that in the velocity time graph. So the velocity time graph below represents the motion of the ball as it bounces vertically on a concrete floor. The time of contact during the bounce is 0.02 seconds, and ignore all effects of air friction. So what is going on here? We had a similar question in the multiple choice, didn't we? Yes, we did. So you have your ball over there and someone just decides to drop it. Okay, so once it drops, it reaches the ground, right? So here we know that our initial velocity is 0. It is at a certain height, definitely, so we don't know what that height is. And if I look at this graph, because we are going from 0 and then it's going all the way positive, it means they have taken upwards as positive. So just indicate that somewhere for yourself that upwards is positive. So they've dropped the ball and then it comes into contact. So those dotted lines, guys, it basically says, or the time between the dotted lines is the contact time it has with the ball. If you were to take a ball bouncing and you took a video of it and you actually saw how that motion looks, you should actually YouTube it, it's quite awesome. It spends some time on the ground, and during that time the ball sort of deforms. Okay, so all that force or that energy, kinetic energy, will transfer to heat energy and sound energy, and also the ball for a moment deforms once it's in contact with the ground. So yeah, at this point this is 0.04 seconds. Then it comes, I'm going to draw a long line, but I mean just for demonstration purposes, it spends 0.02 seconds. Okay, so the time there is 0.42. Yeah, I made a mistake there. So that's 0.4 seconds, and that's 0.42 seconds that it spends on the ground, and then it goes up again. Okay, probably bounces, whatever. Okay, I'm supposed to put dotted lines, but anyway. So at this point here, we know that our velocity is also 0. So at 0.4 seconds, our velocity is 3.92, and then so the final velocity, right? So that's initial velocity, final velocity, and the initial velocity as it leaves the ground, that would be 3.43. And then it goes up again. Okay, so at time 0.77 seconds. Okay, that's where it reaches the velocity of 0, because now it's going to go down again, and it goes down and it reaches the ground at 1.12 seconds. We don't know what the velocity there is. Who knows? Maybe we're going to calculate it. We don't know. So that's basically happening. All right. If I were to draw a displacement time graph, or just in general explaining what's going on. Now, 3.1, define a projectile. Yeah, guys, this is part of theory. So basically a projectile is an object that only has gravity acting on it. Okay, I'm not going to write that down. Let's move on to the calcs. So it says, write down the magnitude of the velocity with which the ball leaves the ground after bouncing. Okay, we've already talked about it. That's basically 3.43 meters. But my goodness, did I write seconds over there? That's velocity, so that's meters per second. Okay, and that's actually a small v. Now it looks like I'm talking about volume. Okay, 3.3. Now draw a labeled free body diagram showing all the forces acting on the ball at 0.77 seconds. So where is it at 0.77 seconds? It's there. Okay, it has reached its highest level after bouncing. Okay, and guys, we're dealing with vertical projectile motion, so the only force acting on it is gravity. because they said ignore the effects of air. Okay, so no air resistance, no air friction over here. So that's basically 50 grams. You don't have to write this. This is just me being me. It's only 2 marks, so that's cool. And then 3.4, it says, use the information on the graph and calculate the acceleration of the ball. Okay, guys. Again. Projectile motion, free fall. Okay, the only acceleration that the ball will encounter is gravitational acceleration, which is 9.8. Okay, that is the answer we are expecting. If you get any answer apart from 9.8, you've done something wrong, hey. But if you get 9.79, I mean, it's close to 9.8, so it's okay. So how are we going to get the acceleration of the ball? Well, if you look at your velocity time graph, the gradient of your velocity time graph is acceleration. Okay, so if I take the first part of this graph, so the gradient here is acceleration. Okay, where you have your change in velocity over your change in time. That's how you'd get acceleration. I don't know if they would give you, if they would give you marks. Oh, but they said calculate. Yeah, you have to calculate. I was gonna say if you just said 9.8, if they would give you marks. But yes, change in velocity. So our final velocity there is 3.92, and our initial is 0. In terms of time, we have 0.4, and then yeah. So if you just calculate that quickly, 3.92 divided by 0.4, 9.8. That's where you hold your heart and you're like, you better be 9.8. Okay, and then 3.4.2. Calculate the height from which the ball was dropped. So basically we are looking for this height over here. If they said after the first bounce, then it would be this height over here. But anyway, they're looking for that height. So we know our initial velocity, we know our final velocity, we know the time that it took. So I'm going to look on the equations of motion in the the formula sheet. I'm going to look for a formula that can give me delta y in terms of initial velocity or final velocity or time, somewhere there. Okay, so yeah, I have delta y is equal to initial velocity, and I have time. There's also this one where final velocity is equal to initial velocity plus 2 times a delta y. I'm going to use the delta y one because it's already the subject of the formula. Okay, but any would work. So we have initial velocity times delta t plus half a delta t squared. Remember, up is positive. Okay, that's what we spoke about initially. Up is positive. That's how they gave us the information. And since up is positive, we know that our gravity always acts downwards. So the acceleration you're going to put there is negative. Okay, so what was our initial velocity there? Initial velocity is 0. Okay, and we said the time we're going to work with is 0.4. And then plus a half, but we have negative 9.8. And then 0.4 squared. So our answer would be, so I have 0.5 times negative 9.8 times 0.4 squared, and that's negative 0.784. And we get a negative answer. What does that mean? Remember, we took upwards as positive, and in which direction is this force going? I mean, this ball going? It's going down, right? So basically, this just means that it is 0.78 meters downwards. Okay, so don't be scared of negative values. Just remind yourself which direction is, what direction are you going to take us up? Basically, if up is positive, if down is positive. Okay, it's up to you to determine. So that is the height from which the ball was dropped. And now 3.5. On a set of axes, draw a position time graph for the motion of the ball from 0 seconds to 1,12 seconds. Use the ground as 0 reference. Okay, indicate the height from which the ball was dropped and all the relevant times on the t-axis of your graph or on your graph. Okay, so we have already drawn it initially, but I mean, if we're just gonna formalize it, it's quite difficult drawing. Okay, okay, this is it. Doesn't matter how it turns out. Okay, so we have our position here. So that's what should I say? So that's t in terms of seconds. Position time graph is gonna say y. So meters. Okay, we can write there time versus position. So we know that this is our ground, right? So we know that at 0,78, this is where our ball was, okay? And then this is gonna be 0,4. I'm gonna exaggerate it a bit. 0,42. So basically it went like this. It's kind of a parabolic graph. Let me do this. Okay. Sorry, my face is in the screen. So, and this space here is quite little. I'll just use a different colored pen. Okay, and then there's that space over there, and then you have okay, so that is at 0,77, and that's 1,12, and that's 0,78. So basically that's it. But if you wanted to, if you have time, that is, you can calculate what this value is. Okay, let me just see if we have everything. Yeah, we do. But yeah, if you wanted to get this value over here, you could calculate it. I'm gonna pause, calculate it quickly because it's not really required, but for 4 marks, if I have time, I would record it. So see you in a sec. Okay, so if you calculated it, still using the same equation to calculate delta y, you would get 0,6. Okay, but like I said, I don't think it's necessary. They just asked for the initial height and the rest of the times. Okay, so that is that. 3.6. Okay, so it says give one term for the rate of change of momentum. Okay, so the rate of change of momentum. So definitely if they mention rate, so it would be P, yeah, momentum is P, which is mv. So rate of change of momentum, it's delta P over delta T. That's what they're asking. What would that be? Okay, I would, if I were you, if I forgot, go to the formula sheet and check. Do we have something like that? Okay, that's net force or resultant force. I don't know if you can see it, but it's this formula over here. So you have delta P. If you divide by delta T, it would be net force. Okay, so yes, that is that, the net force, resultant force. That's your answer. Alright guys, the birds are showing us they are awake. Okay, now 3.7, it says calculate the magnitude of the force exerted by the floor on the ball for the time of contact. Okay, so during this period over here, okay, over here, yeah, calculate the magnitude of the force exerted by the floor on the ball for the time of contact. Okay, so basically we have delta P over here over delta T. We know that our delta T, because the contact was 0.02 seconds. Okay, now what's happening with delta P? Remember delta P that's like change in momentum, right? Impulse, if I could say. So yeah, calculate the magnitude of the force exerted by the flow on the ball. Okay, so net force would be delta P. So momentum is mass times velocity. Ne? So I'm going to say the mass, which is the same, delta V over delta T. Okay, the mass was 50 grams, I think, of the ball. Yes, 50 gram. So that would be 50 times 10 to the negative 3 multiplied by the change in velocity. So at this point we had 3,92. So the final velocity was negative 3,43. Initial velocity was 3,92. And then all of that delta T, so we have 0,42 if you really want to get that specific, minus 0,4. So what is that force? Calculator. Okay, so 50 to the negative 3 times negative 3, negative 3,43 minus 3,92 or over 0,02. So we get 18, negative 18,375. Are we okay with the negative? Let's just look. It says magnitude of the force exerted by the flow on the ball. Okay, because you have the ball and you have the flow. So you have the ball exerting a force on the ground and the ground or the flow exerting a force on the ball. Okay, so but are we done? What we just calculated is the net force. We didn't actually calculate the force exerted by the flow on the ball. So if we were to write our formula, so we have our net force, okay, and then we have the force of the ball itself, the weight, right, of the ball. Okay, and we also have the force of the flow. Put it like this. Force of the flow. Okay, so our net force that we calculated is negative 18,375. The force of gravity, that would be 50 times 10 to the negative 3 times 9,8 plus the force on the flow. So force of the flow on the ball is going to be equal to, okay, so we have negative that and then minus 50 times 10 to the negative 3 times 9,8. Okay, so the final answer is, just shift that and increase that, negative 18,865 Newton. Okay, negative 18,865 Newton, which translate as 18,865 Newton. Okay, they wanted magnitude, yes, so we have to give them the magnitude and not the direction. So yeah, that's basically that for 3,7 and then 3,8. If a softer ball is used and the time of contact with the flow is increased while the change in momentum remains constant, how will it influence the force on the ball? Right? Only increase, decrease, or remains the same. Guys, the moment you increase time, okay, they always ask this question. I think previously they asked, if you have someone throwing a ball and another person catches it, why do they do a motion like that. It's basically to increase the contact time, and if you increase contact time, the force will be less, and therefore your hands won't be hurt. So even here, if you're increasing contact time, it means the force keeps decreasing. Okay, so now they asked how will it influence the force on the ball. Well, the force will decrease. Okay, yeah, and explain your answer. When you increase the time of contact, it will decrease the force that is applied. And you can see here on the formula, if you increase time, your force will decrease. They are inversely proportional. So that's what I would say. And we are done with question 3. Okay, enjoy the rest of your day. Hello everyone, and welcome back to MV Tutors. You're still with me, and we're doing question 4 from the Prelim Physics Gauteng paper. Okay, so yeah, please don't forget to like our videos and subscribe to our channel. Thank you so much for the new subscribers. Thank you for recommending and spreading the word. Please continue spreading it to your classmates, and yeah, let's do this. So question 4, part of the work energy theorem, work energy and power chapter, right? So it says a wooden box slides down a rough 8-meter long inclined plane AB, right? The initial velocity of the box at A is 2 meters per second. So yeah, we can see AB is at an incline, and the angle there is at 30 degrees. So now 4.1 says define a conservative force. Okay, let's just get started there. So question 4.1, what is a conservative force? Okay, so basically it is a force where the work done or the work needed to move an object from point A to B or between 2 points is independent of the path taken. Okay, so yeah, basically if you have a starting point and an end point, and things are happening in between, many things, it doesn't matter because it's independent of the path taken. And examples of that would be like the force of gravity or the force in a spring. Yeah, those are the only 2 that I can actually think of at the moment. So that's a conservative force. Okay, and then 4.2, name the conservative force in the diagram above. Okay, that would be force of gravity. Okay, because I mean for this box, yes, it does have an initial velocity of 2, but from A to B, I mean, gravity is at work. Okay, so force of gravity, I'm just going to say Fg. And then 4.3, state the work energy theorem in words. Okay, work energy theorem. Ooh. Okay, but you get it. Okay, so I decided to just write down the definitions and not leave you out in the cold. But anyway, with the work energy theorem, it's basically the net work done on an object by a net force, okay? And it is equal to the change in kinetic energy of the object. Cool, right? And conservative force, like I said before, there's a definition. On the other hand, a non-conservative force is dependent on the path taken, like we have between A and B. Okay, because we have friction force there, it is a non-conservative force. Okay, because it is dependent on the path taken. Okay, 4.4. The velocity of the block at point B is 6.92 meters per second. Use energy principles only to calculate the frictional force that the block experiences as it moves from point A to B. Okay, so we've spoken about conservative forces. I've also made an example about a non-conservative force. And when you move from A to B, where there is friction, basically, which depends on the path taken, we are dealing with a non-conservative force. So for you to calculate frictional force, you will have to use the non-conservative force formula. Okay, so 4.4. How are we going to get the frictional force? Well, let's go to the formula sheet and have a look at what we can use there. So work, energy, power formulas. Well, we have work done by a non-conservative force is equal to the change in kinetic energy plus the change in potential energy. Okay, let us expand this formula further. If you were to look at work in itself, we do know that work is equal to F times delta X times cos theta. So work of the non-conservative force, we can say that it's actually the friction force, okay, kinetic friction, because it is in motion, and then delta X, okay, the path there, and cos theta. And then delta, or change in kinetic energy, we have half mv squared, but because we're looking at the change in velocity as well, we are going to say final velocity minus initial velocity squared. Guys, please do not make the error of saying we have half m v final minus v initial and you square. That is not the same, okay? It is not the same. Please do not make that error, because now you're just gonna get wrong answers. I remember this one lecturer of ours says that you are committing suicide, basically, because your answers are wrong. You were driving nicely along the road and you decided to jump off the cliff, basically. And it doesn't matter what you did before, you're just gonna get wrong answers. So please be careful of that. And then the formula for what is it? Potential energy, that's mgh. Okay, so mass times gravitational acceleration, and then we have our final height minus our initial height. So getting back to the question so that we can see what values to substitute and what not. Question 4. So they told us that the final velocity, or rather, okay, so friction force is what we're looking for, and then the change in x, I don't really want to use change in x. Maybe let me just say d, to say the distance traveled. So the distance between A and B is 8. If we take upwards as positive, or rather going to the right as positive, going to the left as negative, I'm trying to think, but it's kind of going down. So you can put an 8 there or negative 8, just as long as you remember what you did. And if I were to draw okay, this is basically if my block were to be there, okay, your friction is acting in this direction, and your force of gravity, well, that's if you put it in its components. Obviously Fg is like that, but that would be Fg, yeah, what would it be? Fg cos theta sine theta. It would be Fg sine theta. But anyway, this is the force applied by gravity, okay? But the angle in between the two is actually 180. So here you would use cos 180. If friction was in the same direction as the applied force, then it would be cos 0. But that hardly ever happens. Okay, so you see where the 180 comes from. And then we have half, and the mass is 2. The final velocity is 6,92 squared minus the initial velocity, which is 2 squared, plus 2 times 9,8. Oh, now I shouldn't have erased that. So our height, finally, we know it's going to be 0. But our initial height, if you are again to draw this triangle, remember we have 30 degrees over there. This would be 8, and this is what we are looking for, the height. Ne? So, because I have opposite and hypotenuse, I'm going to use sine so. Ne? Sokatwa, remember? Sine 30 is equal to h over 8. Sine 30 is half, so 8 times a half is 4. Okay, so we have 4 there. Alrighty, so now our only unknown in this formula would be the force of friction. So let's just put everything in the calculator. So we have a half times 2 times 6,92 squared minus 4 plus 2 times 9,8 times negative 4. Okay, and that would be, let me see, so we have 0,5 times 2. Ooh, I forgot a 4 squared over here. Okay, so 0,5 times 2, 6,92 squared minus 2 squared. And then plus 2 times 9,8 times negative 4. So I have negative 34,51. Please keep that answer. Don't switch off the calculator. Negative 34,51 Newton. That is the work. No, that's not Newton. That is joules. Okay, because that is the work done by a non-conservative force. Okay, joules. But on the other end, we have 8 times cos 180. So cos 180 is negative 1. So we have negative 8 times this kinetic friction. That was negative 34. So kinetic friction would then be, if I were to divide by negative 8, I get 4,31. So 4,31 Newton, that is basically the frictional force that the block experiences as it moves from point A to point B. Okay, now we move over to 4.5, where it says the coefficient of friction, the coefficient of friction for the last horizontal stretch after point B is 0,35. Okay, calculate the distance the block will travel before coming to a complete stop without using the equations of motion. Okay, so it comes to a complete stop. All right, so we had from point A to B, and then from point B, okay, so we know that the velocity there at B is 6,92 meters per second, and then it comes to a complete stop at whatever distance that is. Okay, but at that point, because it comes to a complete stop, your final velocity is equal to 0 meters per second. Okay, and the coefficient of friction they gave us, so kinetic friction, I'm gonna assume 0,35. Okay, now calculate the distance the block will travel, and we're not using the equations of motion. Okay guys, what are we going to use here? If we're not using the equations of motion and we're dealing with velocity, the one thing I can think of is kinetic energy. So remember for 4.3, we stated the work energy theorem, where it says the net work done on an object by a net force is equal to the change in kinetic energy of the object. So we will use that. Okay, that the work done, or the net work, is equal to the change in kinetic energy. Okay, so change in kinetic energy, we have half m, so final velocity squared minus initial velocity squared. Okay, and then let's see, what can we do here? We know that the net work is force times displacement. Force times displacement cos theta. Alright. Now let's plug in the values. Okay, so we have half, the mass is still 2, the final velocity is 0, and the initial velocity is 6,92 squared. Okay, and then this side, should have given myself a bit of space, but our force, so D is our only unknown. Okay, so the coefficient of friction, we are basically going to use, so for friction force, we know that we have the normal force times the coefficient of friction. That's what I can think of. And the normal force in this case would be the mass times gravitational acceleration, and then times the coefficient of friction, which is 0.35. So let's just calculate that quickly. We have 2 times 9,8 times 0.35. So that's 6,86. 2 times 9,8 times 0.35. So 6,86 times cos 180 as well. Okay, so that's -1. Oh gosh, I should have given myself some space. Okay, and then times d, so there's a negative there. Alright, so let's just calculate what happens this side. So 0.5 times 2 times -6,92 squared is -47,88. So d is equal to -47,88 all over -6,86. Okay. Alright, so we're going to divide by -6,86. Okay, and then we get the distance is 6,98 meters. Okay, I think that looks cool. I think that is the answer. Yeah, basically that is it. Obviously I don't know, you're gonna write it much better than I, so you probably would have started with that, put it somewhere, and then slot it back in 6,86 Newton, and then slot it back in, and then have it as a negative there. Please don't forget the negative. Let me just actually do this so that I have space for myself. Oh, that didn't really help. Yeah, but basically have a negative there, and then you calculate your distance, and that is it. That is it for question 4, guys. See you chemistry side.
Hello and good day to you. My name is Figa Manana, and we are still doing the prelims physical science paper number 1 of 2022. Now this is the Gauteng version. We are now in question number 5. Well, let's get right into it. It says grade 12 learners conduct an investigation to verify the speed of a race car using the Doppler effect. A race car driving around a race course at constant speed emits a single frequency of 200 Hz. A learner standing on the final straight records the sound using a cell phone as the car approaches him and after passing him. Interestingly enough, my wife and I had gone for kart racing last week, so this is something that we resonate with. And also I'm an F1 fan, so I always watch the F1 races. These cars are very loud, I must tell you that. But in any case, let's just go ahead and read the question. It says, for this investigation, write down the following: a dependent variable. Okay, so what is a dependent variable? Now that means it's a variable that depends on something else. Okay, now there are many things. It could be speed, but because this is a Doppler effect question, if you said speed, yeah, you'd be correct, but a more correct answer would be a frequency, the frequency of the observer, for example. Let's just say frequency of the observer. Okay, that's a more observer. I hope that's how you spell observer. I'm not sure, but this is 5.1.1. And then 5.1.2, one controlled variable. Now, the control variable, when it comes to Doppler effect, it's always like the speed of the wave, and in this instance is actually the speed of sound itself. Okay, so let's just say speed of sound. Speed of sound, the sound speed, that one, it's controlled, it remains constant, it doesn't change. And then a suitable investigative question for this experiment. Now, this is an investigative question that you would ask yourself in this experiment. So it would be things like, what is the relationship between the change in frequency? Okay, let's write that down first. What is the relationship? It's not done because relationship means there should be two or more things, right? Oh, well, you could have a relationship with yourself, but in the context of this question, there should be two things between the change in frequency relative to what? The speed. Frequency relative to the speed of what? Okay, if you say speed of sound, you are wrong. Speed of the car. You have to, because we're dealing with many speeds here, you have to mention which speed you are talking about. Okay, let's do question 5.2 now. There we go, 5.2. Let's read it. It says, when playing back the sound recorded on the cell phone in the presence of an oscilloscope, a difference in frequency of 67.15 Hz was registered. Use the information above to calculate the speed of the race car. Take the speed of sound in the air to be 340. Now, I looked at this question in different ways, and there is not one answer here, because the speed of the car will be different from when the car is approaching and also when the car is leaving, and also when the car is like exactly there with the listener. So it's a bit of a confusing one. Well, let me not say confusing, rather than there might be many answers to it. There's multiple answers to this question. But first of all, what I want to look at, let's take a look at the formula that we'll be using. Now, this is the formula for the frequency of a listener. It's either is leaving, the source is leaving or coming towards. But take a note here, if the source is moving towards the listener, then the Vs is negative. But if is moving away, then the Vs is positive. That's the velocity we're looking for. Now let's take a look at the scenario where the car is approaching, is moving towards the listener. So the formula that we'll be working with then would be the frequency of the listener is equals to V plus or minus VL. That's the velocity of the listener, which is 0 at this point. Okay, let's start with the one. Okay, this is the general formula. Let me just write the general formula. All of this multiplied by the frequency of the source. Now, the actual one that we're going to use, therefore, is frequency of the listener. Now, when it comes to frequency, let's just say towards. Okay, we're working with towards. Now, the velocity of the listener towards will be, if we go back to the question, it said it registered a difference of 67.15, but we know that the frequency of the car is actually emitting 200 hertz. So when it's coming towards the listener, is the frequency increasing or decreasing? It's increasing because it's becoming louder and louder and louder as it comes towards. So we're gonna say that's gonna be that 200 plus the 67.15. That's the frequency of the list. Now when it comes to the formula this side, the velocity here we've been told of A is 340, which is always the case. We're just gonna leave it at 340 because velocity of the listener, or the listener is standing, so there's no velocity there. Okay, divided by same 340. Now what's happening? If we look at the formula once again, it said if it's coming towards, then Vs has to be negative, so we'll have a negative Vs over there. All of this multiplied by the frequency of the sound on its own, and the frequency of the sound on its own and it's emitting, I'll put it on top there, is just 200. Okay, so there we go. All that's left for us to do now is just some mathematical gymnastics. First thing I'm going to do, put this in a calculator. What is 200 plus 67.15? That gets me 267.15. Now what I want to do is get rid of this fraction, so I'll multiply everything with that fraction, which is gonna be 340 minus Vs, and what's left this side is just that 340 times 200. So this is just gymnastics now. If I want to multiply that in, say times 350, it's 340. I'll multiply that in, I get 9831 minus 267.15 Vs. It's going to be equals to that. Should I multiply it in? Okay, just for fun, let's do it. 340 times 200, and then we get 68,000. Okay, so what I want to do now is take all numbers to one side and leave Vs. So if I do that, what I'm going to do is, if I take Vs to the other side, it becomes positive. If I take this number to the other side, it's negative. So I'm just going to say 9831 minus 6800, another 0, that's going to be equals to that, and then I need to divide it by the 267.15. It's equals to 85.46 meters per second. Now this is the answer you get when it's approaching. But if you did this, then you got full marks. You can obviously do the same for when it's moving away. And when it's moving away, the difference is it will be 200 minus 67, because remember the hertz you're hearing as it moves away becomes more faint and faint and faint. So you'll subtract that, and then remember the Vs here for when it's moving away is positive. So you plug those in, and then you will not get the same answer, but your answer will be correct as well. You'll still get full marks for that. And there's a third option where, you know what, let's just leave it at this for simplicity's sake. Still get full marks. Okay, let's do 5.3 now. Now it says the spectrum of light from most stars contains lines corresponding to helium gas. Diagram A shows the helium spectrum as observed in the laboratory. Diagram B shows the helium spectrum of the light from a distant star. Okay, is the distant star moving away from or towards the Earth? Explain your answer. Now listen, let's look at the difference. What's happening here? This is helium on A, that's the star on B. So if you compare the two, especially going towards 700, you can see that the distant star starts stretching, you know, the wavelength, it starts stretching, starts becoming longer, which means that as the wavelength becomes longer, it means the sound is moving away. Okay, so now our answer will be away. Okay, and the reason is because we can see from the spectrum that the wavelength, you know, it's becoming longer. Okay, so let's put that down. The wavelength is becoming longer. It's becoming longer or stretched. You can put stretched. It's becoming longer or stretched, thus meaning the sound is moving away. The source sound, or let's use the words they gave us, thus the distant star is moving away. Star is moving away. That's it. Thank you so much for listening and watching this video. Please like and subscribe to our channel. It helps out a lot to reach out to other learners. And please, if there's something else that you didn't understand or you need extra explanation with, or that you realize we made a mistake on, please write down in the comment section there. Let's engage. Let's find different ways to do this, these questions. Let's help each other, and I would really appreciate that. Well, other than that, I do appreciate you.
Hello everyone, and welcome back to MV Tutors. It's been a minute. We've been getting your comments about, you know, us continuing with the paper. It's just been busy on our side. It's quite busy at work. We're closing down projects, meeting deadlines, submitting assignments for some of us who are also studying. So it's been quite a hectic time, and I decided, you know what, I am tired, but let us make time to complete this memo. Okay, thank you so much for the likes, for the but again, subscribing. I almost said the subscribes and the likes. But yeah, thank you so much for spreading the word. Let's continue doing so that we can deliver a good service to you. Okay, so question 6. Let's see. Alright, it says a small polystyrene sphere B hangs from the ceiling and is attached by a string of negligible mass. 2 other spheres, A and C, are suspended on insulated stands. The charges on each sphere are A with 5,6 nanocoulomb, B negative 2,34, C negative 0,46, and the mass of the sphere B is that kilograms. Assume that the surfaces of all the 3 spheres are conducting. Okay, now let's get to the first question. It says define electric field strength at a point. Okay, Not such a difficult thing to remember or recall, but if you do forget, go to the formula sheet, have a look at what the electric field strength formula is, and from there just try to formulate some words. So if you look at E, that is the electric field strength at a point. So E is equal to F over Q. What is F? It's force. Okay, so it's basically the electric field strength is the force per unit in simple terms. Okay, so just by saying that force per unit charge, not just per unit, force per unit charge, then you get 1 point. But if you want the full definition, it has to be per force per unit positive charge at a point, and. So yeah, let's get back here. So for 2 marks, I thought let me just write it down so that we don't spend time writing the definition. It's basically electrostatic force. Okay, so keyword there, electrostatic force, not just any force, electrostatic force experienced per unit positive charge. Okay, it's another thing, per unit positive charge placed at a point. So those 3 key words, electrostatic force. Okay, meaning it's not 3 words. 3 phases. Electrostatic force per unit positive charge. Yeah, okay, cool. 6.2, it says sketch the electric field pattern around sphere B and C if A was removed. So A is the positive one where B is attracting itself to, hence you can see with the string the tension force. So now if A is removed, you have B and C. Okay, they are still going to repel each other because they are negative forces. So we have B here and you have a negative for C. And then when you draw electric field lines, okay, so first of all, when they come from the surface, it's quite perpendicular. Then it will start to curve. Okay, so perpendicular and then it curves, perpendicular, curves, and so forth and so on. Okay, but yeah, I don't know how strict they'll be marking you on it or showing the perpendicular portion of it. So it's perpendicular. And also the arrows, when it's negative, the arrow is going inwards. Okay, so that's B with its negative, and then you get C where it's well positive, just goes out. And okay, this is me exaggerating, but this is pretty much. And because C is a bigger number, 7,46, you might want to add more, but I don't think it would really matter much because ultimately, okay, B, I drew it a bit bigger. Ultimately, they are both nanocoulomb. Okay, so I don't think it would matter. But if you wanted to illustrate that you understand that the bigger the charge, if it's negative or positive, the more field lines you will have. And don't forget the arrows. Okay, now 6.3. Charge B experiences a net force of 0,04 Newton due to charges A and C. No pun intended. Find the distance R between charges B and C. So you would firstly get the force, okay, of A on B, right? Because it's an attractive force. And then you get the force of C on B, okay, which is a repulsive kind of force. C on B. Or B on C, I guess maybe it doesn't matter. Okay, and when you add those two forces up, you actually get your net force. Okay, so that's how we're going to tackle this one. They told us that the net force that B experiences is 0,004078. Okay, and then the force of A on B, you can go to your formula sheet just to determine what that formula says. So we're gonna get our constant. I'm just gonna write it up here. So we have K, Q, yeah, let's just say Q1, Q2 over R squared. So that is the formula. So now getting to A and B, let's go back. Okay, so A on B, you have your constant K, which is 9 times 10 to the power 9. For A, we have a charge of 5,6 times 10 to the negative 9. And then B, we have 2,34 times 10 to the negative 9. Okay, we're gonna add, oh, that is all over R squared, which is 6 times 10 to the negative 3 squared. Then we add the force of C on B. So again, we have 9 times 10 to the 9 times 7,46 times 10 to the negative 9 times 2,34 times 10 to the negative 9. And that is all over R squared because that is what we are looking for. We're looking for R, the distance between the charges B and C. Okay, so what can we do then? We can take this whole term, okay, and take it to the other side. Then we are left with that with R squared. Then we can take R squared to the other side and bring that whole term underneath here. I'm sure you're like, what the hell? So if you have x is equal to y plus 2 over r, and we're trying to get r, I'm saying, firstly, you're going to take that side. So I'm going to have x minus y, and I have 2 over r. Then because I want r, I'm going to have to say r goes that side, and then 2 over x minus y. That's what that's what I mean. Okay, I'm just thinking of a way of just putting everything in the calculator. Hence, I'm just, going all about. I mean, this is after all physics, so they are assuming you can do the maths, right? So this is not a maths lesson. We're just really trying to get the radius. So the radius squared will then be 9 times 10 to the 9 times 7,46 times 10 to the negative 9 times 2,34 times 10 to the power negative 9. And all of that is equal to 0,004078 minus 9 times 10 to the 9 times 5,6 times 10 to the negative 9 times 2,34 times 10 to the negative 9. And to finally get r, we're going to have to put all of this in the calculator. Obviously, we're going to take the positive value of r. Okay, so let us see, what do we get? So, you see the danger in doing all of this is if you make a silly mistake, then everything is wrong. The beauty, however, is that they will give you all the marks except the answer. If your answer is wrong, probably going to subtract a mark or something. But they can see the maths and they know you probably made a stupid mistake. So 9 times 10 to the 9 times 5,6, and this saves time, but only if you get it right, hey? Okay, we are getting wrong answers here. Oh, what did I do here? So 9 times 10 to the 9, 7,46, negative 9 times 2, negative 9, minus 9 times 10 to the 9 times 5,6 times 10 to the negative 9. This should be negative 9. No, this is not working out. 7,46, 10 to the next. You see, that's where the danger lies. Now here I am with values that are not making sense. Okay, let's try this again. 9 times 10 to the 9 times 7,46 times 10 to the negative 9 times 2,34 times 10 to the negative 9. So we get 1,57, 1076 times 10 to the negative 7 all over okay, let me see. Oh, I forgot, guys. I forgot to divide by the 6 times 10 to the negative 3. Okay, I'm going back to what I did previously. It's not there. I refuse. 7,46 times 10 to the negative 9 times 2,34 times 10 to the negative 9. Okay, cool. Then we have 0,004078 minus 9 times 10 to the 9 times 5,6 times 10 to the negative 9 times 2,34 times 10 to the negative 9 all over 6 times 10 to the negative 3, and that is squared. Whew. Okay. Yeah, now we're getting a reasonable answer. Okay, so we can erase all of that. We have our answer. 1,399. I'm just going to say 1,4 times 10 to the negative 2 meters. If you take this to that side, yeah, okay, so it's going to be 0,14. Okay, no, let me do it like this. 14 times 10 to the negative 3 meters. Okay, yeah, does that make sense though? Yeah, I mean, if the distance between A and B is 6 millimeters, then I guess this one can be 14 millimeters. Ne? All right, so we are almost there. So 6,4. Charges A and B are allowed to touch and then move back to the original distance between them, the 6 millimeters. Now, calculate the new charge on each sphere. So if you would remember, if spheres are going to touch, they will share the amount of electrons or their charge, and then when you take them apart, they each have an equal portion. All right, so basically you're getting the average between A and B. So the new charge, Q nu, will be the charge of A plus the charge of B. We're getting the average. Yes, we are. So what is the charge of A? It is, now this is where you have to put in the sign, okay? This is not a time to be modest. So we have negative 2,34 times 10 to the negative 9, and that is all over 2. Actually, it was not necessary for me to add the times 10 to the negative 9, but it's fine. So 5,6 times 10 to the negative 9 minus 2,34 times 10 to the negative 9 all over 2. So I get positive 1,63 times 10 to the negative 9. Why am I writing 3? Okay, and that is coulomb. Okay, we're not forgetting the unit. All right, so that is the charge on each sphere. The new charge, now 6.4.2, almost there, says, explain the change, if any, to the field pattern between B and C. Now remember, the charge on B is now positive, right? The charge on C is negative. So as such, they will have an attractive, remember that is at 90 degrees, so they will have an attractive charge to them, okay? And then, yeah, you know the drill. So these are the new field lines, where you have it going from positive to negative, okay? I think they might give you marks for illustrating. They didn't ask us to illustrate, but if you are a visual learner, just like me, you would like to demonstrate or illustrate, not demonstrate. So it says explain the change, if any, to the field pattern. So now there will be a force of attraction between B and C, first and foremost. Yeah, because now B is positive, 1,63 times 10 to the 9, while C is negative. And I would just end it there. Okay, and that's it for question 6. Hello and welcome back to NV Tutors. I'm Tsul and I'll be looking at question 7 with you guys. You know the drill. Please don't forget to like our videos, subscribe to our channel, click on the notification bell so that you are notified when we release any more of the questions, the memo. Alright, so let us look at question 7. So it says, in the circuit below, the battery has an EMF of 24 volts and an internal resistance of 0.6 ohm. The heater has a resistance of 10 ohm and the fixed resistor has a resistance of 30 ohm. The variable resistor can change between 0 and 15. Okay? Alright, so let's get to the question. It says the variable resistor R is set at a resistance of 3.5 ohm. Alright, so now we know what's happening. Now it says calculate the total resistance of the circuit including the battery. Okay, so what are we going to do? If we were to just sketch this out ourselves, so we have the ammeter there. First of all, the heater and the resistance of 30 ohm, they are parallel to each other. So I want to get the equivalent parallel resistance, right? Then we have that variable resistance, which is set to 3.5 ohm. And then we have that internal resistance, okay, just a small r, which is equal to what? 0.6 ohm. So I think, yeah, let's first work out what the parallel resistance is. But that's a simplified version of this circuit. So if we start first with the parallel, remember it is 1 over the parallel, and we had 1 over 10 plus 1 over 30. Okay, if we take the common denominator is 30, then I would have to multiply by 3 there, and then that's just 1. So I have 4 over 30, and then here just 1 over parallel resistance, so that would be equal to 30 over 4. So 30 divided by 2 is 15. 15 divided by 2 is 7.5. Okay. But please always use the calculator. So we're not done. We just got the parallel resistance, which is 7.5. But our total resistance, which is what they want, we have 7.5 plus 3.5, which is 11, plus 0.6, which makes it 11,6 ohm. All right, and that is that. Oh, really? 5 marks. Did I do less things? Okay, I think it's 11,6. Now 7,1,2. It says the current measured by ammeter A2. Okay, so again we have, all right, let me just draw it out here. So there we have our circuit there. We want to know what is A1 first and foremost. Then whatever current you have there at A1, we're going to work it out. It divides, okay? It divides into A2, and it also goes there. It's going to pass the 30 ohm resistance, passes the heater. Okay, and then it joins up again. Okay, so we need to know at this point how much of this, let's say A1 is 3 amperes, I'm just making an example. How much of the 3 amperes goes to A2, and how much of the 3 amperes goes to the 10 ohm resistor, and how much of it goes to the 30 ohm resistor. Okay, and there is a formula, right, that has been worked, or that you do know of. Let's say we had an ammeter here called A3. Okay, so if you wanted to get A2, the current going to A2, okay, I'm just gonna say this is your I, and then here you have, I wanna maybe say small I. Okay, so you have maybe here I2 and here I3. How would we work it out? The current at 2, you're basically gonna take that 3 and you're gonna multiply it by a ratio. And what is that ratio? Well, I know in the denominator I have A2 plus A3. No, not A2, what am I saying? I have the 10 plus the 30, and I want to know what A2 is. Okay, so I take the total amperes that is going through the circuit, and once it divides, I just want to know what A2 will be. So I know that in total I have 10 plus 30 ohms, all right? But what do I put on my numerator? Do I put the 10 or do I put the 30? First of all, look at this. Your current, when it passes through the 10 ohm, that current, will it be more or less than when it passes through the 30 ohm? Remember, the higher the resistance, the lower the current. So we're expecting a lower current here and a higher current there. So if you were to put 10, you are calculating the lower current. But if you put 30, you're calculating the higher current. Okay, so that will be our formula. But firstly, we need to determine what the current is. They gave us the EMF, right? Remember, EMF is equal to the current where we have the resistance in the circuit and the internal resistance. So they gave us the EMF, it is 24. Okay, we don't know what the current is. And we know that the resistance in total, basically R plus small r, we calculated it, it is 11,6. Okay, so now we can get what the current is, the total current. So 24 divided by 11,6, okay, we get 2,07 amperes. So that is our total current. Now getting back to this formula, let's just use a different colored pen. So this is our formula here to get what the total current is. And now we're going to take this formula, take it down. Okay. Yeah, this is where you start. So the current at 2, we have the total current which is 2,07. Hopefully you did not delete that from the calculator. And then we have 30 over 40, which is just 3 over 4. So that's 75% of it. So we get our answer. Oh no. So equal to, and then our answer times 0,75. So we get 1,55. There's more than one way of calculating the current. You could have used V is equal to IR. Okay, there are a lot of ways, but this is the one way I'm gonna look at. Other people who have done it differently, please comment down below so that when other viewers get to see it, they can see other answers. Okay, we're working together. So yeah, let's do that. So now we have 1,55 amperes. Yeah. Okay, 7.2. The variable resistor is now adjusted to have an even higher resistance value. So now we go from 3.5 to a higher value like 5 or 7 or 8, whatever. Now it says, how will this affect the power dissipated by the heater? So will it increase, decrease, or remain the same? And explain the answer by using a suitable equation. So if we go to our formula sheet, yeah, so basically we have that the power is equal to the voltage times I, all right? And we know that voltage is IR. Then we have the I, so we have the, okay, I'm repeating that we have I squared R, okay? So, and we also have power is equal to V squared over R. Okay, so if you were, just look at this. So this is what we're focusing on. I'm going to look at two of them because either way we should get the same answer. If I were to increase resistance, it went from 3.5 to a higher value, the power will decrease. Okay, this equation sets it out quite nicely because I can see clearly that increase in R will be a decrease in P. Okay, so P is inversely proportional to R. What about here? If you were to increase R, you would say, well, an increase in R means an increase in power, right? But when you increase your resistance, you are decreasing your current. And if you decrease your current, which is squared, it holds a bigger weight. So decreasing the current squared will also decrease the power. Okay, let's just go back to the question. So how will the increase in resistance affect the power dissipated by the heater? It will decrease it. Okay, why? Because power in this instant is inversely proportional to the resistance. All right, and we have made this, explained this answer by using a suitable equation. You could have used this one or that one, and it works either way. Okay, so yeah, that is it. See you again on another question, whenever that is. But yeah, thank you for tuning in, and more is to come. Hello everyone, and welcome to MV Tutors. I'm Solo, and I'll be looking at question 8 with you guys. Please don't forget the drill of liking, subscribing, clicking on the notification bell, informing your classmates that yeah, we are busy addressing the prelims and preparing for final exams. Okay, so yeah, we're going to look at question 8. So it says, learners perform an experiment to determine the internal resistance of a battery. They use a variable resistor as the external resistance as shown in the diagram below. Now, switch S is closed, okay? Readings from the voltmeter and ammeter are recorded after each change of the resistor. So you can see in this table, we have 5 experiments that when the current increases, all right, because if you are variating, is it such a word? When your resistance is variable, busy changing, whether if it's increasing, your current will decrease. If it's decrease in your current will increase. So you're busy, changing your resistor up and down because it's a variable resistor. So we can see that as the current increases, the potential difference in the cell decreases. Remember though that the EMF is always the same. Please do not ever take that the EMF is decreasing or increasing. It always remains the same. Now it says, use the information in the table above to plot a graph of potential difference versus current. And I want to ask you, which one goes to the y-axis and which one goes to the x-axis? Remember, the x-axis is the independent variable, the y-axis is the dependent variable. What I would say is, which one depends on the other? Remember, if switch S is open, there is no current, and therefore the potential difference will always read the EMF. But as soon as switch S is closed, there is current, okay? So the current will flow, all right, in the circuit. The current, how strong the current will become depends on the resistor. But the potential difference, if you can recall, really does depend on the current and the resistor, okay, or the resistance. So I would put the potential difference as the dependent variable on the y-axis and your current in this case on the independent, as the independent variable on your x-axis. All right, so we can plot. I have put the graph and we'll see what we can work out. Okay, let me just change the color of the pen and we can go ahead and plot. So when current is 0, we have our potential difference as 1,5. So we can plot it there. When the current is 131, we have 1,3. So 1,3 is somewhere there. Maybe 131 is somewhere there. I don't know. This is not drawn to scale. You, on the other hand, had graph paper, so you should be drawing approximately the correct values. 229, 1,15. Okay, 1,15. So that's probably somewhere there. And 229. Guys, I'm just gonna estimate. Okay. All right. Oof. 327 with 1. Okay. It's gonna be somewhere there. Okay, so 1, we have 327. Maybe it's gonna be somewhere here. And then finally 652 and 0,5. So maybe it's somewhere there. Okay, and then we're gonna plot a line of best fit. All right, I would want my first and my last to to be part of that line. So yeah, that is our line of best fit, guys. We tried, hey. So yeah, let me just reduce that. Okay, so there's our graph, and we can go ahead and answer the questions. 8.2.1. Okay, 8.2.1. Use the graph to determine the EMF of the battery. Well, the EMF, we don't even need to draw the graph to see it. As long as there's no current flowing, you will determine from your voltmeter what the EMF is, which is 1,5. All right, but I will get to the graph. Okay, so we know that the EMF is 1,5 volts. The y-axis, the intercept of the y-axis actually does give you, sorry, this thing is supposed to reduce to that. Okay, so yeah, the y-intercept will be your EMF. All right, if you're going to plot the graph of potential difference versus current, it will always across the y-axis, and you'll get your EMF. Okay, now it says calculate or determine the internal resistance. So if you know, or if it has been communicated to you in class, you would know that the gradient of your graph, which is a negative gradient, you can see it goes down from left to right. So your change in potential difference and your change in current will give you your internal resistance. Okay. Yeah. And also, if you wanted to determine it using the EMF formula, it would go as follows. So remember, EMF is equal to the potential difference in your circuit plus your lost volts, right? And your lost volts would indicate the current through the circuit and your internal resistance. And then you have your EMF there. So if you were to put everything in terms of potential difference, you would get that your EMF is minus, I'm just going to put R in front, okay? And because we know that the EMF is the y-intercept, I'm just going to put it like this, because we have a straight line. So we have negative RIV. Okay, so if you have your straight line graph, remember y is equal to mx plus c. We know EMF is your y-intercept, and negative R, because obviously the gradient is going down, would be your gradient, which is what we just said. Okay, so we can then solve, or rather get what the internal resistance is, change in V over change in I. Now if you have a graph like this where you have points that are off the graph, all right, and you had your line of best fit, I think, yeah, actually these points, because I didn't draw it to scale, they should actually just shift down. But what you can do, you can always use your first and your last coordinates. Okay, so your first coordinate is 0 and 1,5. Your final or last coordinate is 652 amperes. So it's just times 10 to the negative 3, and your potential difference is 0,5. So you can just use that just to be on the safe side. Okay, so I would then have 0,5 minus 1,5. And for 0,5, I have 652 times 10 to the negative 3. Please don't forget that it is milliamperes. Okay, and then at 1,5, we had 0 milliamperes. So if we work that out, we would get, so 0,5 minus 1,5. The answer that you're going to get is going to be negative. But please, when you report the internal resistance, you can't report it as a negative number. You have to take it as positive, okay? What does that even mean to say you got a resistance of negative whatever? Okay, so no, it has to be an absolute value. So 652 times 10 to the negative 3, and we get our answer as negative 1,53. But what you end up reporting is 1,53 ohm. Okay, resistance is an ohm. Okay, is this it? Oh, there's a short question. So 8.3, a conducting wire of negligible resistance is connected between the points X and Y. Okay, so does it mean that variable resistance and ammeter are taken out? So it's connected between the points of X and Y, just the conducting wire. How does this affect the temperature of the battery? Okay, write down increase, decrease, or remain the same. So, if you are going to put a conducting wire between X and Y, okay, I'm assuming that this variable resistor is moved now or something. Okay, so now the temperature of the battery, remember the internal resistance is at the battery, okay? So if you have a high resistance, then your temperature will decrease. If you have a low resistance, then your temperature will increase. So now if we're just going to have a conducting wire between X and Y without that variable resistor, it means your resistance overall has decreased. And if your resistance has decreased, your current will increase. And if that's the case, the temperature of the battery will increase as well. So battery temperature will increase. Okay, so yeah, it basically is explained by the fact that the resistance overall has decreased. As a result, your current has increased, and then the temperature of the battery will also increase. Okay, so that's it for question 8. I'll see you guys question 9. Hello everyone and welcome back to MV Tutors. I'm Tsolo and I'll be taking you through question 9. Alright, don't forget to like our videos, subscribe to our channel, click on the notification bell. Alle goeders, okay? So yeah, the diagram below shows a simple model of a DC motor. Alright, we can see here we have the magnets north to south. We have our split ring. The ring is split, so split ring commutator. We have our battery source there. Okay, so 9.1, it says describe the energy change that occurs in a DC motor. Okay, if you forget what happens, think about a car in a motor. What am I saying? A car is a motor, but basically a motor, you take electrical energy and from the electrical energy you get motion happening. So electrical to mechanical. Okay, a generator, we cannot forget what a generator does because Eskom has been doing us bad. So generator is from mechanical to electrical. So if you forget what a motor does, think about what a generator does and apply the inverse for a motor. So we're going to go electrical for a motor, electrical energy to mechanical energy. Mechanical energy. Okay, that's how we get cars moving. Then 9.2, explain the term DC. Well, DC, that is direct current, right? And direct current, basically, it tells us that our current is moving or flows in one direction. It's not like alternating current where it can decide in the middle of nowhere. Okay, not really, but it alternates. Okay, flows in one direction, then it alternates its direction. Okay, flows in one direction. Obviously, you're going to write it out much better than I did there, but that's a simplified explanation. Or definition rather. 9.3, in which direction will the conventional current in the coil flow? So will we have our current flowing anti-clockwise, SRQP, or clockwise, PQRS? Okay, so they just asked in terms of P to Q or from Q to P. With generators, I hope I'm telling the truth here. We are going to use our right hand rule, okay? Where your thumb indicates the thrust, your index finger indicates the, from north to south, okay? And then your middle finger indicates the direction of the current. But with motors, we use the left hand rule. Alright, so we can see from north to south, we go from left to right. And then we don't know anything about the thrust. They didn't tell us. So whether if the thrust is up, then your current will flow clockwise. But if your thrust is down, then your current will flow anti-clockwise. So in this case, we don't know anything about the thrust. We just know that it goes from north to south in that direction. But what will actually give us a good idea is the battery. So you have a negative terminal, positive, negative, positive, negative, positive. Okay, then you connect to the split ring commutator and then it goes all the way to the wire. Let's just go straight to the wire. Okay, so let's just say this is our wire here. It's not fully correct because we have taken out the split ring commutator. It's split, right, this commutator, so that you only have current in one direction. So in this case, you have SRQP. So if you want to know in which direction it will go, you know your current from your battery source, it flows from the positive to the negative, okay? So it will go in that direction. So ultimately it goes from Q to P. So we will go Q to P. And then 9.4. Explain the change that needs to be made for this motor to be an AC motor. Okay, so for a DC motor, for a DC motor we have a split ring commutator. This portion here, it's split, right? And that makes sure that the current flows in one direction. But for it now to be an AC motor, we're going to have a slip ring commutator. It won't be split anymore. It will slip right in. Okay, never mind. But anyway, it will be, you're going to need a slip ring, not a split. Okay, so yeah, play of word. There you have a split ring commutator. Here you have a slip ring commutator. So that is what will assist us in getting this motor to be an alternating current motor, to get a slip ring. Okay. And finally, a heater labeled 2000 watts. So we know it's some kind of power. And 50 hertz. So that's your frequency. Okay. With the frequency, you can always get, what do you call this? Yeah, you can always get your, geez, I forgot what T stands for. My bad. But yeah, I will remember in a second. Okay, it's connected to an AC circuit. So, period. Yes, it stands for period. Calculate the maximum current that flows through the heater. So I suggest we go to the formula sheet and get the equations there. Okay, so we have our P average. Oh, did they give us our voltage somewhere? Yes, 220 VRMS. 220 volts. Okay, so yes, so we have our formula here that says our average power is equal to root mean squared volt and current root mean square. So we have our average power, we have VRMS, we can get what IRMS is. This is going to be P over V. Okay, so our average power is 2000 watt and our RMS voltage, that's going to be 220. I'm definitely going to use the calculator. 2000 divided by 220. So it is 9,09091. Okay. So that's just the IRMS. That's not what they asked for. Answer is in amperes. They asked for the maximum. Okay, so we know that IRMS is equal to the maximum current over root 2. So the maximum current is equal to root 2 times 9,091. So without removing the answer from the calculator, we are going to take that value and multiply it by root 2. And we get 1,28, or rather 1,29 times 10, which is just really going to be 12,86. Yeah, amperes. Okay. I'm not sure, was that the last question? I think so. Yeah, We didn't even need to use the frequency. But yeah, we have the maximum current flowing through the heater, and that concludes question 9. Hello everyone and welcome back to MV Tutors. You'll be excited to know we are finally doing question 10. We are finally done with the paper, guys. It took a while. Thank you for being patient with us, and yeah, let's grow this channel. Alright, so question 10. Don't forget to like our videos, subscribe to our channel, the whole drill, you know. So it says a photoelectric cell is connected in a circuit. The lowest frequency of light that will emit electrons from its cesium surface is 5,1 times 10 to the 14 hertz. Okay, violet light has a wavelength of 400 nanometers and is incident on the cesium surface. I think cesium has on the periodic table it's Cs. I don't know, you can correct me. Okay, so you can see there, and this frequency that they've given us, I hope you've seen or noticed that that is actually the threshold frequency. Okay, and I see actually the first question wants us to define what threshold frequency is, and basically that is the frequency or the minimum frequency that is required to start emitting electrons from the metal surface. Okay, or a specific metal surface, because you have different threshold frequencies depending on the type of metal that you have. Okay, so threshold frequency, first of all, it is your minimum frequency that is required to emit electrons. Minimum frequency, I'm just going to write keywords. Minimum frequency required to emit electrons. Yeah, I'm writing electrons. Electrons from a particular metal surface. It has to be a particular one. Can't be the same metal surface, or yeah, basically, like I said, threshold frequencies depend on a certain kind of metal surface. Okay, 10.2.1, calculations, which I like personally. So it says calculate the work function of cesium. So work function, let's just see the formula for it. I think I missed it. Oh, there we go. So work function is, I think that's Planck's constant times your threshold frequency, and we know that H, Planck's constant, is 6,63. This paper actually wasn't so bad, now that I think of it. So yeah, anyway, that's 6,63 times 10 to the negative 34, and then we go to the threshold frequency. They gave it to us, which is 5,1 times 10 to the 14. Paper 1 wasn't entirely bad. As I reflect, I just hope then, because they normally make prelims hard compared to the finals, so let's hope that if this is like the hardest, then that's great. It means the finals won't be that hectic, but study as though they will be more hectic than this. Okay, look through a whole lot of past papers and get your bearings in order. Just suss out what you don't understand at the moment and address it now. Please don't leave it for the night before. It's not good. So we get an answer, the work function, and this is work, so it is measured in joules. Okay, times 10 to the negative 19 joules. Okay, so let's just get rid of the calculator for now. And now 10.2.2. Okay, so what we're calculating there, it says the amount of energy carried by the incident photons of wavelight. Remember, the threshold frequency is enough to just emit the electrons from the metal surface, okay? But for those electrons to start moving, because just ejecting or emitting them means you've opened the door and they are out. Now what? We need energy to start walking or running or whatever. Okay, so now we're going to calculate that amount of energy carried by the incident photons. Okay, so now let us go and get the energy formula. So E is equal to something. Okay, we just calculated. So there are two formulas. We have one with maximum kinetic energy. We don't know the kinetic energy, so we're not going to use that one. Then we have one where it is Planck's constant times frequency. Okay, did they give us? They gave us the threshold frequency, okay? Not any other frequencies. So you can't use the threshold frequency in this instant, or else we're just working out the work function. So let's see. What can we do? What else was given to us? So apart from the frequency, we were given the wavelength. All right, and we can do something with wavelength. If you have forgotten, just want to check if they gave us a formula. Yes, so if you have V is equal to frequency times wavelength, so it's basically, your velocity. But in this case, we're going to say the speed of light. Okay, so we're going to use C rather instead of V. Okay, so we have C. And if we want to put all of this in terms of frequency, because we have frequency here, so we're going to say frequency is equal to the speed of light divided by the wavelength. And then we're going to plug it back here. So we have Planck's constant times C all over the wavelength, and then we can get our energy that we're gonna measure in joules. Okay, so Planck's constant, we already written it before, 6,63 times 10 to the negative 34 times the speed of light, which is 3 times, okay, this is something we noted on the side, so 3 times 10 to the power 8 meters per second. And all of that is divided by the wavelength. I think they said 400. Yeah, 400 nanometers. So 400 times 10 to the negative 9. Okay. And then we're just going to calculate it there real quick. Okay, 6,63 times 10 to the negative 34. Times 3 times 10 to the 8 all over 400 times 10 to the negative 9, and we get 4,97 times 10 to the negative 19. 4,97 times 10 to the negative 19 joules. Okay, so our work function was 3,38. Okay, it's just the minimum energy that they had, but for them to actually start, doing something, rising up, whatever, 4,97. The kinetic energy is the one that's actually required to, get them moving. So the maximum kinetic energy of the photoelectrons emitted from the cesium surface when violet light shines on it. Okay, so So basically work function, energy needed to just wake them up. Then we had the energy carried by each photon, and now for it to move, for it to run, we actually need the kinetic energy. So sorry about my previous explanation there, but hopefully this makes sense. Okay, so we need the kinetic energy, and we saw the formula pertaining to the kinetic energy. So we have it as energy is equal to our work function, which we've already determined, plus the maximum kinetic energy. So our maximum kinetic energy is actually equal to the energy minus the work function. So the energy that we got there is 4,97 times 10 to the negative 19, and that's minus the work function, 3,38. You know I'm an advocate for saving answers so that your answers are not saving your answers in the calculator so that your final answers are not watered down. But I can imagine sometimes, you don't think about saving, so it's fine. You will be given marks. They definitely won't take that away from you. Okay, so let's see. What will the answer be? So we have that, and we are subtracting 3,38 times 10 to the negative 19. And we have 1,59 times 10 to the negative 19 joules. Okay, and then what do we have next? Last question, 10.3. The practical application, it says give one application other than a voltaic cell which makes use of the particle nature of light. Okay, guys. I would suggest solar panels that generate electricity because really the government and Eskom are really screwing us over at this point. So we have the alternative of using solar power, right? Not so easy, not so cheap, but it's a good investment, I believe, overall. But Eskom now wants to punish those who want to use the sun. Anyway, politics story for another day. So I would use it for solar panels. Okay, for the generation of electricity. And that concludes the physics paper. So we'll be seeing you guys for chemistry. Okay, hopefully our schedules don't get as busy and we can just get it out of the way and you can be free to prepare for your finals. Bye.